Assalamu alaikum. This is lecture 10 of data security and encryption, and in this lecture we are going to discuss about some mathematical concepts about finite fields. Finite fields have become increasingly important in cryptography, and a number of cryptographic algorithms rely heavily on properties of finite fields. Most importantly, the advanced encryption standard and elliptical cryptography algorithms use the concepts and implementations of finite fields. Other examples that include the incorporation of finite fields are known as method authentication code systems and authenticated encryption schemes. So this lecture will provide you a background on the concepts of finite fields to and it will be able you to understand the designs of advanced encryption standards and other cryptographic algorithms that use the finite fields. It is understood that many of you will not be familiar with the abstract concepts of algebra, and it is very difficult to grasp the concepts of finite field without the proper background of mathematics and algebraic theory. Therefore, I will try to go as slow as possible, and I will hope that you will be able to understand the finite field concepts. So before any further discussion, let's have a look at the contents of this lecture. In this lecture, we are going to discuss some fundamental concepts of mathematics known as groups. There are two kinds of groups in number theory known as abelian and cyclic groups. Then there are rings, fields, and finite fields of the form GF. There are finite fields of the order P known as the prime number, and this lecture will also provide a way to find out the multiplicative inverse in a finite field. So at the end of this chapter, you should be able to distinguish among groups, rings, and fields, and you should be able to define a field in the form of a GF into P. Fields are actually a subset of a larger class of algebraic structures called rings, which are in turn a subset of a larger class called groups. Groups are defined by a simple set of properties, and it is very easy to understand the concept of group. Each successive subset known as abelian group or a cyclic group or a ring or a commutative ring adds additional properties and it makes it more complex. Finite fields are a subset of a fields consisting of those fields with a finite number of elements. These are the class of fields that are found in cryptographic algorithms. This image highlights the origination of finite fields, that from where the finite fields came from. So as discussed in the last slide, the main algebraic elements are called groups, and there is a further definition of abelian groups, rings, domains, and fields, and in the fields we have finite fields, which is the topic of discussion for this lecture. Groups, rings, and fields are fundamental elements of branch of mathematics known as abstract algebra, or sometimes referred as modern algebra. In abstract algebra, we are more concerned with the sets on which elements we can operate algebraically. That is, we can combine two elements of a set, perhaps in several ways, to obtain the third element of a set. This can be done by the specific rules such as the rule of addition, subtraction, multiplication, division, permutation, or any other arithmetic operator. So let's start from groups. Group referred as G is a set of elements with a binary operation denoted by dot that associates each ordered pair. For example, we have elements of a group A and B, and we apply this operator dot, and we get another element that must be part of the group G in such a way that the following axioms are obeyed. So before proceeding forward, let's define what an operator dot is. So dot operator is a generic representation of an operator, and it can refer to the any operator in the mathematical operations such as addition, subtraction, multiplication, division, etc. So for elements to be in a group, uh, there must be some properties that or axioms that must be obeyed. So first axiom states that it is a closure axiom. It states that if A and B both elements belong to G, and then you perform any operator such as A plus B or A minus B, and if the resulting item is also in the G, your elements are in a group. Similarly, it must obey the associative property. For example, if you apply the operator on A dot B dot C, it must be equal to A dot B dot C, and all the including elements such as A, B, C must be in the group G. And it must also hold the identity element, that is, there is an element E in the G such that if you multiply with any element A, the result will be A, such as identity for multiplication is 1. If you multiply any number by 1, there is no change, and if you add 0 to any number, there will be no change. So the fourth property states that for each A element in a group, there is an element A1 in the group such that if you apply the operation A with the A1, there must be a reverse operation A1 operated by A. There must be some element E known as identity. So that means there should be an inverse of each element in the group to be that satisfy. For example, if you have uh, for example, if you took the multiplicative inverse, for example 2 multiplied by 1 by 2, and it will result in the identity element 1. So if a group has a finite number of elements, it is referred as finite group, and the order of group is equal to the number of elements in the group. However, if the elements are not finite, the group is called an infinite group. So for a group to be an abelian group, it must satisfy an additional condition, and that additional condition is a commutative property that states that A dot B, any operator, is equal to B dot A, and it should hold for all A and B in the G. So for example, the set of all integers positive, negative, and 0 under addition is an abelian group. That means it will hold all the property. That means both the elements A and B will belong to set group G, and it will hold for the associative property because you are using the same numbers for multiplication or addition or any other operator. Similarly, if you have the positive and the negative numbers for and the 0 in the set, you will have the identity element for each of the number. Similarly, if you have positive and negative numbers, you will have the inverse element for the each number, and the commutative property will hold for each number. So apart from the abelian group, the other group type is a cyclic group. Cyclic group refers to the exponentiation, and it is defined within a group as repeated application of the group operator. For example, if we want to specify the a cube, we can specify it with a dot a dot a. For this example, dot refers to the multiplicative operator. Similarly, we define a raised to power 0 as identity. That means if we take the power of any number with the 0, we get the identity element. And a raised to power minus n will be equal to a inverse power n, where a is the inverse element of a group. This can be verified. For example, if you take for example a is equal to 2 and you take the cube and you have the operator here 2 cross 2 cross 2. Similarly, for the same case, you take the identity element. For example, again we take the element 2 and take the power 0, that must be equal to 1. So 1 is the identity element for multiplication here. Again we take the value of 2 and we take the value of n as any random number. We take 2 raised to power minus 3, that will be equal to 1 by 8. And similarly, on the other hand, if we take the inverse of 2, that will be equal to 1 by 2, and we take the power 3, again it will be equal to 1 by 8. So a group is a cyclic group if every element of G is a power of an element A raised to power k. K is an integer of fixed element and A belongs to group elements G. So if we hold this property, then our group will be a cycle. In simple words, if every element can be represented with a power a raised to power k, then your group is a cyclic group. The element A is said to generate the group G or to be generator of group G. For example, if you have element 1 or 2 and you take the power of each with each k integer, the resultant items will be elements of that group G, and the A, the number you are taking power from, will be said to the generator of group G. That means it is producing the actual group G. A cyclic group is always abelian and may be finite or infinite. So you can have a finite or infinite group in a cyclic form. So that defines the group on the whole. Let's move to the other definition, rings. A ring R is said to be defined as R plus multiply in a set form is a set of elements with two binary operations known as addition and multiplication, such that for all A, B, C in a ring R of the following axioms are obeyed. So again, if our ring must hold all the 5 axioms of the group, that must be that the R is an abelian group with respect to addition, that R suffices the axiom A1 through A5 discussed on the slide number 5. For the case of an additive group, we denote the identity element as 0 and inverse element of A as minus A, and it must specify or hold further axioms known as closure under multiplication. So it states that if A and B belong to R, then AB is also an R. That means if you multiply two numbers from a ring, then the result will be also a part of a ring. Another property it must hold is associative property. That means if you multiply A with B and C, it must be equal to A multiplied by B, and that result will be multiplied by the C for all elements belonging to a ring. And it also holds the distributive law for addition and subtraction, that for any element to be in a ring, it must hold the distributive law. So in essence, a ring is a set in which we can do addition, subtraction and multiplication without leaving the set. That means all the elements, all whatever elements you take from the ring, and you perform the operation of addition, subtraction and multiplication, the result will be in the ring itself, and you do not have to take any elements outside the ring. So with respect to the addition and multiplication, the set of all n square matrices over the real number is a simple ring. Additionally, for a ring is said to be a commutative if it satisfies the one additional property or a condition known as commutativity of multiplication, which is very simple property. States that A multiplied by B must be equal to B multiplied by A for all elements belonging to ring. So the set of integers specified by a set Z ranging from 0 to n minus 1. If you take the arithmetic operations of modulus with the n which each element of set, the resulting values will be a commutative ring. Next is a definition of integral domain, which is a commutative ring that obeys the following axiom. The first axiom is the multiplicative identity, and then second is the no zero divisor. The first axiom states that there is an element 1 in the ring such that if you multiply with any element to the element 1, the result will not change. So if such property holds for the ring, and with the another property that there is no zero divisor for any elements A or B in R. If you multiply both and the result will be 0, then either A is 0 or B is 0. So there must be no zero divisors. So this property should not hold for a list, for a ring to be integral domain. So for example, for any list or set of integers known as positive, negative and 0, under the usual operations of addition, multiplication, the list or set will be an integral domain. So if you reach further down, you meet the definition of fields. A field F, sometimes denoted as similar to the ring, and it is denoted as F additive and multiplication, is a set of elements with two binary operations called addition, multiplication, such that for all elements A, B or C in the F, the following axioms are obeyed. So again, it must hold all the axioms for the groups, and it must hold all the axioms for the rings. So F is an field is an integral domain. That means it must satisfy all the above properties. F satisfies axioms from A1 through A5 and M1 through M6. Additionally, it must uh, hold another property known as multiplicative inverse. So it states that for each element A in the F except 0, there is an element A inverse in F such that if you multiply both, the result will be identity. So it states that for a classification of a field, there must be a multiplicative inverse for every element except 0. So in essence, a field is a set of which we can do addition, subtraction, multiplication and division without leaving the set. That means if you perform any operations, any of the listed operation on the values of your field, the result will be also from the set of the field. So division is defined with the following rules, such as A divided by B is written as A into B inverse. So familiar example of fields are rational numbers, the real numbers and the complex numbers. Note that the set of all integers is not a field because not every element of the set has a multiplicative inverse. So here are the properties and axioms that defines the groups, rings and fields. So you have clearly seen the definition of group, and there were only three or four properties for classification of an elements to be in a group, known as closure under addition, associativity of addition, additive identity and additive inverse. So if elements hold these properties, they are referred as a group of elements. So if the elements hold the commutative addition, the group is known as abelian group. Similarly, if the simple properties of multiplication such as closure, associativity and distributive law hold, the set is referred as ring, and if another property such as commutative property of multiplication exists, the ring is known as commutative ring. Further, if you specify the multiplicative identity and no zero divisors, your list is your ring is a integral domain, and if your integral domain holds the multiplicative inverse property of every element except number 0, your set will be referred as a field. So at this moment we have defined a field as a set that obeys all of the axioms described in the last slide. So infinite fields that are not of the particular interest in the context of cryptography. However, there are two types of finite fields as illustrated in this figure, known as finite field with p elements, p is a prime number, and finite field with the p raised to power n elements. So we are going to discuss both in the upcoming slides. So finite fields play a crucial role in many cryptographic algorithms such as advanced encryption standards, and it can be shown that the order of finite field must be a power of prime number raised to power n, where n is a positive integer. So it states that the finite field of order p raised to power n is generally written as gf into p raised to power n. So gf stands for Galileo's field, in honor of the mathematician who first studied the finite field. So for n is equal to 1, we have finite fields of gf of p as mentioned here. This is the finite field and has a different structure than the finite field with n greater than 1. This lecture introduces to the finite fields of this form, such as gf into p. However, this form of field will be covered in the next lecture. So if you look at the finite fields described for the addition modulus 8 and 7, if you look at the right hand side of the picture, it defines the modulus fields of number 7, and if you look at the left hand side, it defines the addition modulo 8. So So you can see the properties we specified for the fields such as commutative addition and the inverse properties exist for addition for the number 8 and the number 7 respectively. So that means all the property hold for the additions, such as you have the a pattern here similarly discussed in the lecture 5 or 4 of this course. These are the fields of order 8 and 7 using the modular arithmetic modulus of 8 and 7 respectively. So as it can be seen, it satisfies all the properties required for a field. But now if you compare the same modulus 8 and 7 for the multiplication, you can see the left hand side of this figure is represented by the modulus of 8 and the right hand figure is represented by the modulus 7. So in the latter case we can see that uh, the field of Z8 using the modular arithmetic 8 is not a field because it does not have the multiplicative inverse for each of the element described here. On the other hand, if you see that the uh, properties of uh, field 7 have the multiplicative inverse of each of the element holding the rest of the properties. So for example, you can take any of the two values. For example, if we look, we did not have the multiplicative inverse for the number 4. So we take the value 4 here and we multiply with each of the number and we get here 4 multiplied by 2 and we divide by the 7 and we get the modulus 1. Similarly, we didn't have the modulus of 8 here, so it's modulus of 6 here, and if we take value of 6 multiplied by 6 gets 36 and the modulus will be 1. So this is evident here that additive and multiplicative inverse of modulus 8 and 7. So you are very familiar with this table you have seen in the lecture number 4. This defines the additive inverse and this defines the multiplicative inverse for the modulus 8 field. So additive inverse for exists for the each of the number and multiplicative inverse exists for few of the numbers in modulus 8. However, our other properties stated that except for the 0, multiplicative should exist for the each of the numbers. In this case, it is very easy to find the multiplicative inverse of any element from the Gaussian field for a prime number p for small values of p. However, for the large values of p, it is very difficult and it is very impractical to calculate in such manner. So if you are dealing with such kind of problems, you can use the equation mentioned in the lecture number 5 that showed us to solve the extended Euclidean algorithm, and the equation was written as ax plus by is equal to any number d, which was the greatest common divisor of a comma b. So in this case, if you get by mod a is equal to 1, then y is the b inverse. So at this point you can apply the extended Euclidean algorithm and this will yield the value of multiplicative inverse of b if the GCD of a comma b results to 1. So if you recall the example done in the lecture number 5 for the extended Euclidean algorithm, you have seen two values we taken. For A was 1759 and for B it was 550. So by using the equations for the extended Euclidean algorithm, the solution of equation was 1759x plus 550 where y is equal to d, and which yields the value of y is equal to 355, and b inverse will be equal to 355 as stated, where y will be equal to b inverse. So for this verification you can calculate 550 multiplied by 355 and taking the modulus 1759 as we stated in the a little while ago, that b multiplied by y, and you take the mod with the a, and the value of a is 1759, you get the result that is equal to 1. So it holds the extended Euclidean property. So in general terms, the extended Euclidean algorithm can be used to find a multiplicative inverse of any number in the set or a field. If we apply the extended Euclidean algorithm to the equation ax plus by is equal to d, the algorithm yields d is equal to 1, then y will be equal to b inverse in the set or a field. So to conclude this lecture, it is summarized in the finite field of order p, where p is a prime. So it shows that how to construct a finite field of order p where p is prime with the following properties. The first property states that the gf of p consists of p elements. For example, if you have seen the above two examples, the gf of 7 exists of 7 elements. Similarly, the another property states that the binary operations plus and multiply are defined over the set. If you take the example of 7 modulus, the addition and the subtraction operations are defined on the set. The operations of addition, subtraction, multiplication and division can be performed without leaving the set. So each element of the set other than the 0 has the multiplicative inverse. So it was also evident from the example. So the elements of GF of P are the integers from 0 to P minus 1, such as in 7 modulus we had 0 to 6, and the arithmetic operations are addition and multiplication mod P. This concludes today's lecture. In this lecture, we discussed some mathematical concepts about the groups of abelian groups and its cyclic groups, and we narrowed it down to the definition of rings and fields, and we discussed the finite field of the form of the G f of P. So we had the finite fields of order P, and we looked at the formula to find out the multiplicative inverse in the finite fields. So if you want to study more, you can look at the chapter number 5 of recommended question. You can ask me through any designated medium, or you can create a question and answer session. Thank you very much.